Well, hello there, AP Physics. Once again, I'm fixing a mistake. What can I say? All right, so when it comes to rotation number 6, this final problem, I don't know what happened to my brain. It turned into some gelatinous goo, and I ended up saying a whole bunch of not very smart things, and then I corrected myself, and I still made mistakes. So it was pointed out to me. I decided, hopefully when you looked at the rotation 6 video, I tried to go in and say like to trim it, but there was something in the video editor, like once it was already uploaded, I couldn't figure it out. So I said, I'll just put in there, don't pay attention after 11 minutes and 30 seconds, and I'm going to fix the problem. So here we are. Here we are with this question. Let's see if third time is a charm, and we can actually do something that looks a little bit like physics today. So let's talk about this physical situation. As you can see, I've already copied the numbers out of my particular question, but let's look at the basics here. So guy's sitting on his stool, spinning around, holding his arms out. And then just like the ice skaters you've seen at the Olympics, when they pull their arms in, they start to spin faster and faster, and he would do the same thing. Okay, so what we know is that whatever his final kinetic energy is going to be when he pulls his arms in, it's going to be greater than his initial kinetic energy, because we're going to change his inertia, right? The inertia is going to drop as he pulls his arms in. And here, while, whatever that number is comparatively to something else, but it's still larger than when he pulls his arms in. So that's the basic idea, right? So if our inertia drops and so on, we are going to see an increase in his speed, and comparatively his initial velocity will be lower, angular velocity will be lower than when he pulls his arms in. Okay, so why is this happening? Here's why this is happening, and I swear I'm going to say it right this time, everybody. Promise, I promise. When he is spinning in the first place, he has an angular momentum. His angular momentum is the inertia of the guy plus the inertia of the weights and his speed. Okay, now he is not colliding with something else. However, once you have an angular momentum, in order to change that angular momentum, you have to apply an outside torque. Nothing's happening here except the guy moving his arms. There's no extra push. He's not attached to like some rotating thing that's going to make him spin faster. None of that nonsense is going on. So his initial angular momentum will equal his final angular momentum as like I said here. So this relationship actually, well, not for that one, right? This one is my initial, right? He's got a higher inertia, and so he'll have a lower velocity. This value will remain the same, and so then when he changes his inertia and it drops, his speed will increase. And of course, that will affect his kinetic energy. So ignore what I said before about that saying the same. That doesn't make any sense at all. What was I doing? Don't know. Okay, now let's get down to some nitty gritty here. All right, so what would be wise, I think, is to figure out the momentum of this guy as he is moving, right? So we got to figure out the initial momentum of our person. To do that, we better figure this baby out. This we've already been given. So the guy with the stool, and he's given a number. I appreciate that very much. All right, so there's an actual numerical value there. There's not just some weird formula, because what would the formula for some guy sitting on the stool be? I don't know. But what I do know is that if I have 2 or more objects, I got to add those inertias together. And that's exactly what we have to do here. So the student plus the stool plus the inertia from one arm plus the inertia from the other arm, because you got 2 arms. We're going to assume they're the same. Yes, you could multiply it by 2. I'm just going to write it all out here. Okay. We are going to consider the weight on the end of his arm to be a point mass. Perfect? Maybe not, but close enough, good enough. So mr squared for the one arm, mr squared for the other arm, and we're going to add that to this inertia. Okay? Hopefully you are better on the calculator than I am. I had to do this calculation 3 times because I kept hitting the wrong buttons. Why am I not surprised? All right, so my total inertia to start with is going to be higher than the final inertia, but I do need to find it. That will let me, with my angular velocity, help me find my angular momentum. Why do I need that? I need that for when I pull the arms in. However, once I know the inertia to start with, I can certainly find the kinetic energy before, right? Our kinetic energy formula is pretty close. It's got the same stuff in it as we know. So, certainly take your initial angular velocity here, the inertia you've just calculated, and figure out, what letter is that? What number is that? It's like B1. So before. Now, to do part A, where you find the new angular speed of the student, again, let's remember this inertia or this angular momentum, once you find it, is not changing because we are not applying an outside torque to the system. It's also not crashing into something else. Like there's nothing weird going on here. So like, let's say, for example, you got 100 for this. It's not, but let's just pretend, right? That means that after he pulls his arms in, of course, he has the same angular momentum of 100. And now that you're going to recalculate the inertia, you'll find the new angular speed. Okay, so that's the game plan here. All right. Once you find the original momentum, once you find the original kinetic energy, I would redo the inertia calculation, right, with the new radius for the arms, and then you'll have a new lower inertia. You'll be able to then set that equal to, you're going to be able to apply this into the momentum formula on the new angular speed. That, of course, will let you find part A. It will also let you find part B. Okay, I think that made some coherent sense. Good luck. I'm so sorry. I'll talk to you guys later. Have a great rest of your day.